Hello. Today I'm going to be talking about Booleans in Mathematica. The first thing we should talk about are the Boolean values, true and false. So, things that you do in programming languages is to determine if an expression or an input is true or false. In Mathematica, those two concepts, the concepts of logic true and logic false, are represented using these predefined concepts of true and false. The key idea is that those are the logic ideas of true and false, and they're not the same things as the strings true and false. So if we evaluate this, true and false, this true and this false, they're just saying that when you see something that says true, it's true. When you see something that's false, that's this false with the capital F, that's false. With those ideas, you can start to you can do truth tables and other concepts from logic. So one thing is that if you want to negate an expression, you can use the exclamation mark in front of the expression. And so not true, when you evaluate that, you get false. When you evaluate not false, you get true. Another thing that you might do with true and false values is you might want to verify that everything is true. That's when you use the AND operator, and you might want to verify that at least one of them is true, and that's when you would use the OR operator. So for instance, if we do something that's true and something that's true and something that's true and something that's true, because all of them are true, you get true. But if one of them is false, if one of those pieces is false, then not all of them are true, so this evaluates to false. Similarly, for OR, if everything is false, if this, we want to check to see if this, or this, or this, or this, and if all of them are false, then it evaluates to false. Whereas if at least one of them is true, then this OR statement, this OR grouping will evaluate to true. Okay, so that's true and false. The next thing where do you get true and false values from? Well, you'll get them when you compare two quantities. So if you have two quantities and you want to see if the first quantity is less than the second quantity, or less than or equal to the second quantity, or equal to the quantity, or greater than or equal to the quantity, or greater than a quantity, you're comparing two things and you want to ask the computer, are they equal? How are they compared? That's when you will get an answer that's true or false. So if we typed in here 10 is greater than 5, that's true, but 5 is greater than 10, false. This greater than or equals to sign, if you type in for less than or equal to 2, you can see that Mathematica changed that less than or equal to into a less than or equal to symbol. And again, if we evaluate this, 4 is not less than or equal to 2, so that's false. But 2 is less than or equal to 2, so that would be true. The key thing to know about these comparison operators is that you have to use a double equals instead of a single equals to test whether two things are equal. So remember, a single equals sign is used to define variables. A double equals sign is basically asking a question. So I will say equals equals, and I sort of think of it as mathematicians like to use this question mark over equals. Are these two equal? So whenever you see a double equals, read it as a question. So when we write down x is equal to 4, that's defining the variable x to be equal to 4. If we evaluate x equals 4, that's going to say true, because this variable x, we're asking the question, is x equal to 4? Because we defined x to be 4, this is now true. As a quick example, which is larger, 2.2 to the 3.3 or 3.3 to the 2.2? Well, if we do 2.2 to the 3.3, and let's just ask, is that greater than 3.3 to the 2.2? That's false. So that's saying that, in fact, 3.3 to the 2.2 is bigger than 2.2 to the 3.3. All right. So another place where we get true and false as answers to an evaluation is a bunch of these Q commands. So when you see a command that ends in Q, then you should think that's a question. So for example, this even Q is a command that determines if a number is even or not. So I'm going to evaluate these three examples. We want to know, is 3 even? Is 4 even? Is the square root of 2 even? So 3 is an odd number. It is not even, so it evaluates to false. 4 is equal to 2 times 2. It's an even number, so even Q of 4 is true. And then the square root of 2 is not an integer, so it's not even, so even Q gives false. Another one of these is prime Q. So the command prime Q determines if a number is prime. So if the number is prime, it will give true. If it's not prime, it will, if it's not a prime integer, then it will not give true. Or it'll give false, excuse me. So prime Q of 1 is not a prime number. 55 is not a prime number, it's 5 times 11. And if you didn't know this, 1,234,577 is indeed a prime. All right, so if you go to the testing expressions guide, we can click here, the testing expressions guide, we'll see, you can see a number of these commands that end in Q. For example, I think the thing that I like to use the most is member Q. So check to see if you've got an element of a list in there. So explore those, see what kind of Q functions there are. Let's do some true-false questions. So you might want to see, so 31 is prime, is 2 to the 31 minus 1 prime? Well, to figure that out, we use prime Q of 2 to the 31 minus 1, and that is a prime. But for the next prime number, 37, 2 to the 37th minus 1 is not prime. All right, is e to the I pi an integer? So the question about whether you're an integer or not is using integer Q. So then e to the I pi is e to the I times pi. Remember, all of these need to be capitalized because they're predefined in Mathematica. We evaluate that, and it's true. E I pi, well, if you knew some polar coordinates, this might not surprise you because e to the I pi is actually -1, so it is an integer. Here's one more example. Is the number 91 one of the first 100 prime numbers? So let's create a list of the first 100 prime numbers. Primes is equal to the table of prime of I, where I goes to 100. All right, we could have written prime, map prime to the range from 1 to 100. But here's, oops, what did I do? I forgot my I, not 1. This is our list of primes. We could just look at it, but maybe this is all, maybe it's not easy to see. Let's just evaluate this, and now we want to ask, is this true? Is the number 91 a member of the list primes? And so we saw our list, 89 is a prime and 97 is a prime, but 91, if we did factor integer of 91, we could see that 91 is 7 times 13, so it's not prime. All right, so the last bit for this section is to use an if statement. So the key idea for if statements is that you should use an if statement to make an output depend on a condition. And if statements are the natural habitat of these comparison operators. So the place where you often use or see Q commands or comparison operators is inside an if statement. So how does an if statement work? When you type in if of a condition, an expression, and an expression, Mathematica evaluates the condition. And so this condition is it raining? Right? All these different things. It's a question. And if it's true, it'll do the first thing. And if it's false, it will do the second thing. So here's an example. Let's define z to be equal to 10. And here's an if statement. The if statement says, if z squared is less than 50, then say z is a small number. Otherwise, say z is a large number. So if we type in z is equal to 10, and we check 10 squared is 100, that is not less than 50, so z is large. But if we typed in z is equal to pi, then pi squared is about 10. Pi squared is less than 50, so z is small. So let's do a couple of examples. First example is you can use an if statement to let's use an if statement to define a function absolute value that gives the absolute value of an input. So how does absolute value work? So we want to define, we have an input, we'll bring in x, and we'll say if x is less than 0, so if x is greater than or equal to 0, then we want the answer to be x, right? The absolute value of a positive number, or 0, doesn't change x. But if x is not greater than or equal to 0, then we actually want, so negative 2, we want to change it to positive 2, so that's multiplying by negative 1. So this function here now checks, it looks at the input, sees if it's greater than 0. If so, the output is x. Otherwise, the answer is negative x. So the absolute value of 4 is going to be 4. The absolute value of negative 42 is going to be positive 42. The last thing that I would say, especially for people who have programmed before, you may have been used to using if, else, or nested if statements. In Mathematica, you can use the which command instead of nested if statements. So let's look at this example. Here is a way to determine what letter grade you would get for different numerical percentage grades. So if you got a 90 or above, you would get an A. If you got an 80 or above, so if not, then you would evaluate this, which says, oh, if you're not 90 or above, but if you're 80 or above, then you're between 80 and 90, so you should get a B. But if you're not 90 or above and you're not 80 or above, then you're under 80. So we kind of need to figure out, wait a minute, but are you bigger than 70? So if you're not greater than 80, then we have to check, are you greater than 70? And if so, you're between 70 and 80, so you would get a C. And if you're not above 70, then we have to ask another question, is your grade above 60? And if so, you would get a D, otherwise you get an F. So this is a statement that would evaluate. So let's plug in a grade. So if you had an 87.5, then you evaluate this. You're not bigger than 90, so you don't get an A. But now if you're bigger than 80, you get a B, so you got a B. And similarly, if you had plugged in 69.99999, well, that is not greater than 70, but it is greater than 60, so you would receive a D. So let's say instead of using a nested if statements, we can use a which command. So what we do is we do which, and we say, okay, the way which works is you give a condition. So I'm going to do a lot of copying here, so let me just copy most of the expression here. You give an expression. If the expression is satisfied, you get the first thing. Otherwise, it checks the next condition, and it sees if that's satisfied, and it would give you the next thing. And then it checks to see the next condition, sees if that's satisfied. And then the last bit is we need to give one more expression that would be the if everything else fails. One way to do that is just to do an underscore. And so now this expression does the exact same thing as this nested if statement, but there's a lot less brackets, there's a lot less things you have to keep track of, and if you set it up like this, then you can really see what's happening. Alright, so that's all for this tutorial on Booleans. See you later.